3, 2, 1. And we are on the air, ready to talk about inverse matrices. Now, I first introduced these creatures back in an exercise in Chapter 3, specifically in Exercise 23 of Chapter 3. But now that we are in Chapter 4 and have a full section on inverse matrices, I figured it was time to say a few words about them in a video. So let's start with the basics. If A is a square matrix, then it might or might not have an inverse, which is a matrix B that undoes the action of A, and conversely, which is itself undone by A. Or stated algebraically, the matrix product BA would have to be equal to, well, let's think this through. This matrix product is a matrix in its own right, and it works through composition of linear maps. So what happens? We feed something into A, A's output then becomes the input for B, and whatever the output of that is going to be the output of this full product, BA. But if B is A's inverse, then B undoes A's action. So whatever vector we feed into A in the first place, all right, A turns it into something else, and then what does B do? Well, it turns it right back into whatever it was to begin with. So the net effect of BA is to not change anything about the vectors that it eats. That means that BA is the matrix representation of the do-nothing linear map. And we know that the matrix representation of the do-nothing map is the identity matrix. So if B is A's inverse, then B times A is equal to the identity matrix. But we also said that to be an inverse, not only does B undo A, but B is undone by A. A undoes B, which means that the matrix product AB must also be equal to the identity matrix. And for the same reason, if A and B are inverses of one another, they undo each other's action. So if you feed a vector to B, and then the output is passed along to A, well, A just undoes the action of B, and its output is the same as the original input, which means that this composite map, this matrix product AB, doesn't actually do anything. It corresponds to the do-nothing map, whose matrix representation is, of course, the identity matrix, with ones on the main diagonal and zeros elsewhere. Finally, some notation. If A has such an inverse, it need not have one, but if it does, we call it by this symbol, which we pronounce A inverse, just an A with a little -1 exponent, the same kind of notation we use for inverses of functions. Thus, the general statement would be that when you multiply A and A inverse together in either order, you get the same thing, namely, you get the identity matrix. All right, so now we know the definition of an inverse matrix. Let's consider a concrete example. If R is a matrix representation of a 90-degree counterclockwise rotation, and here I mean a rotation about the origin in R2, is that matrix R invertible? And if so, can we actually find what the inverse, R inverse, will be? Start with the first question. Is it invertible? Don't think about this algebraic stuff. R is a matrix. It represents a linear map. Can this linear map of 90-degree rotation be undone? If so, then R is invertible. If not, it isn't. Well, of course it can be undone. The way you undo a 90-degree counterclockwise rotation is to rotate 90 degrees clockwise. Nothing deep here. So yes, R would be invertible, and R inverse would just be the matrix representation of a 90-degree clockwise rotation about the origin, which is easy to write down. In fact, let's go ahead and write down the matrices for R and R inverse. We'll start with R. This is a map from R2 to R2, so we're going to have a 2x2 matrix, where the columns correspond to the images of the standard basis vectors. Namely, the first column will be the image of I hat. Well, what happens to I hat when we rotate it 90 degrees counterclockwise? Of course, it becomes J hat, whose components are 0, 1, and column 2 is the image of the second standard basis, J hat. Well, what happens to it when we rotate 90 degrees? Of course, it becomes minus I hat, or in other words, -1, 0. So far, so easy. And R inverse is no more difficult. Its first column is the image of I hat, but now under a 90-degree clockwise rotation, which transforms I hat into minus J hat, which is 0, -1. Similarly, the second column is the image of J hat under a 90-degree clockwise rotation, which of course is going to be I hat, which is 1, 0. And we have computed our first inverse matrix. And in this case, we got it just by thinking about what was happening geometrically. That won't always be the case. We will develop an actual algorithm for computing the inverse of any invertible matrix. But before we get to that, the important thing is just to understand the ideas of what an inverse matrix is actually doing. But here, having computed this inverse matrix with our bare hands from first principles, we might as well go ahead and verify that what we said should happen algebraically really does happen. So let's take the product of these two matrices in either order. I'll compute R times R inverse. Well, the product of these two 2x2 matrices is going to be another 2x2 matrix. And when we compute its entries in the usual way, we do indeed find that the product will be the identity matrix as claimed. And I will leave it to you to verify that if you had computed that product in the opposite direction, you would have obtained the identity matrix as well. So once again, we see the nice interaction between the geometry, thinking about rotations undoing one another, and the algebra. Good. But it's important to remember that not every matrix has an inverse. If I have some square matrix, it might be invertible, like that rotation matrix we just considered, but it might not be invertible. And I'll give you an example of a non-invertible matrix where we can see the non-invertibility geometrically. Let P represent an orthogonal projection of R2 onto the x-axis. Now, what's an orthogonal projection, you might ask? We will have lots to say about these things when we get to Chapter 8, where we will be discussing them in a very wide context. But in this very narrow context, it's very easy to understand. The idea is that if we're working in R2 and we have a point in R2, if we project it orthogonally onto the x-axis, what that means is that we will simply drop a perpendicular to the x-axis, and the point where that perpendicular hits the x-axis will be the image of our original point under the projection. Orthogonal is really just a highfalutin way of saying perpendicular, but you get the idea. If we had some other point in R2, where does it get mapped by this orthogonal projection? Right here. And if we have a few more points, well, it's obvious where they get mapped to. Now, a projection is a linear map, so it can be represented by a matrix. We can have a 2x2 matrix, since this is a map that takes vectors in R2, like this one, and sends them to vectors in R2, like this one. And of course, we can write down the matrix in the usual way. The first column is the projected image of I hat. Well, where does I hat go under the projection? Well, I hat corresponds to a point that is already on the horizontal axis, so it doesn't move. The projection fixes I hat. So I hat's image is still I hat, 1, 0. And the second column will be the projected image of J hat. Now, what happens to J hat under the projection? Well, J hat corresponds to the point 0, 1, which of course is projected to the origin. So the second column becomes 0, 0. And the question I want to ask is this matrix invertible? Well, let's think about it. In other words, is this linear map invertible? Is this function invertible? Well, what has to be true for a function to be invertible? Here, let me carve off a little section here. Let's go back to the pre-calculus dungeon. Hell, forget about inverses altogether. What does it mean for something to be a function? Because that question is really at the root of all this stuff we're talking about, even if it doesn't seem like that initially. So let's start down here and we'll build back up to it. What does it mean to be a function? The hallmark of functionality is summed up in the phrase, one in, one out. You drop one thing into the function and you get one thing out of the function as a result. Like in pre-calculus, you drop one number into, say, the squaring function, you get one number out. If you drop 9 in, you get 81 out. If you drop -12 in, you get 144 out. It's a function. In order for an inverse function to exist, it must do two things, and those two things are given by its name. It must be an inverse. It must invert a function, and it must be a function. In order to exist, it still has to satisfy the one in, one out condition. For example, consider the cubing function. You stick 2 in, and you get the number 8 out. No ambiguities. 1 in, 1 out. You put the number 3 in, and you get the number -27 out. You put the number 1/2 in, and again, there's no ambiguity. You are going to get 1/8 out. Okay, so the cubing function is a perfectly good function, but we can invert that function. It has an inverse because if we take any output of the function, any one output, I can tell you exactly one input that produced it. What produced 8? It must have been 2. What produced minus 27? It must have been minus 3. What produced 1 over 8? It must have been a half. And that inverse operation, of course, is what we call the cube root function. It inverts what the cubing function does, and it's a genuine function. For every one thing that goes in, we get one thing that comes out. The only difference is that we are reversing all those arrows and calling the function the cube root function. This is in total contrast to something like the absolute value function. Now that's a perfectly good function. You put 5 in, you get 5 out. You put minus 3 in, you get positive 3 out. There's never any ambiguity. Whatever you put in, you know there's one and only one thing that comes out. It is not, however, an invertible function. The absolute value does not have an inverse, because when we try to invert it, turning the outputs into inputs, and vice versa, it fails this one in, one out condition. It's not a function at all. For example, if I say, okay, we're going to go backwards. I got out a 3. What must have been put in to get the 3? You can't just say, oh, well, it must have been a minus 3, because it could have been positive 3. So there's an ambiguity. If we try to go backwards, going forward, everything's fine. I know what happens to minus 3. It becomes 3. I know what happens to plus 3. It becomes 3. But go backwards, what gave me 3? I don't know. Might have been minus 3, might have been plus 3. So there is no inverse to the absolute value function. Anyway, the reason for this seeming digression down here in the precalculus dungeon is because we can apply the same logic to our projection matrix, or rather the underlying projection itself. Is it invertible? Well, to have an inverse matrix means that it has an inverse function, namely an inverse to that linear map. Is this projection invertible? Given the outputs of the projection, can I reconstruct the inputs unambiguously? No, of course I can't. Because if you give me, say, this point right here, and say, well, what was the one and only one thing that could have been projected to that point? Well, it's not just this. It could have been this point, i.e. this vector, or this point, i.e. this vector. All of these points, or equivalently all of those vectors, get mapped to this point or vector. And in fact, there are infinitely many others that could have been projected to that point. Anything on that particular vertical line would do the job. That means that the linear map cannot be undone. It cannot be inverted. The projection is not invertible, and therefore, obviously, the matrix, which merely represents the projection, is not invertible. So here too, we see this geometrically, where it's obvious. The algebraic reflection is that there is no matrix that you can multiply on either the left or right of P and come up with the identity matrix. But I bring this example up just to have a concrete case of a non-invertible matrix. Not all matrices are invertible. In the universe of all matrices, only some are square, and of those square matrices, only some are invertible. Incidentally, it's a reasonable question to ask, well, why do we have to restrict our attention to square matrices in the first place? Okay, I've seen that not all square matrices have inverses, but isn't it possible that some non-square matrix has an inverse as well? I mean, why did we toss all the non-square matrices aside right off the starting line? Was that over hasty? No, it wasn't. It is actually impossible for a non-square matrix to be invertible, and there are a few different ways to see this. I outline one way in the solutions to one part of that exercise back in chapter 3 that I mentioned, exercise 23, I believe. But I'll try to give you another way of seeing why a matrix has to be square to possibly have an inverse here in this video. I think I can show you in a more geometric way that will actually relate to the kind of stuff we were just talking about in thinking about the one in, one out condition to be a function. Because again, to be invertible, that means some kind of inverse function. You still have to satisfy one in, one out. So let's just imagine for a second that we have some matrix A that is not a square matrix. Let's say it's a 2 by 3 matrix. So that's a short fat matrix, like so, where I've just put stars for whatever numbers they might be. Well, this matrix would represent a map from, well, let's see, it's a 2 by 3 matrix, so it would represent a map from R3 to R2. And we remember why that is. The input vector would consist of weights for the 3 columns. So it would have to have 3 entries. That means it would be a member of R3. And the output of that matrix vector multiplication is just a weighted sum of those 3 columns. Well, each column lives in R2, so a weighted sum of R2 vectors is going to be another vector in R2. Okay, anyway, I've got this non-square matrix. We said it represents a map from R3 to R2. So let's just think geometrically what that would be like so I can show you why it can't be invertible. So this matrix, this map, acts on R3, and it takes vectors in R3 and maps them to vectors or points, however you want to think about it, in R2. Now, one thing we know, without knowing anything about the specific entries of the matrix, is that it's mapping all of R3, a 3-dimensional space. It's smushing it into a 2-dimensional space. That means there has to be some serious dimensional collapse that occurs during the mapping. Presumably, R3 gets mapped to the entirety of R2, in which case it's losing only 1 dimension, but it could be more extreme than that. All of R3 could get mapped to some subspace of R2, like maybe everything in R3 gets mapped by A to a line through the origin, a 1-dimensional subspace of R2, in which case 2 dimensions are getting crushed out. Or it could be more extreme than that. It could be that all of R3 gets mapped to the trivial subspace, the origin, a 0-dimensional subspace, in which case all 3 dimensions are getting crushed by the map. In any of those scenarios where we have that dimensional collapse, we're going to get many things over here getting mapped to the same place over here. That is inevitable. And once that happens, we will not have an invertible map. We won't be able to get back, because if 2 things over here get mapped to the same place, and we want to ask, well, where did that come from? We won't know. It will no longer be unambiguous. It could be from here, or it could be from here, or it could be from maybe somewhere else. Let me try to make this even more concrete. We know that a linear map, or matrix that represents it, is a grid transformation. It acts on the standard basis vectors of the domain, and everything else gets dragged along for the ride. So let's suppose that this matrix, this map A, takes the standard basis vectors I, j, and k and sends them to, say, these 3 vectors in R2, which I'm calling I prime, j prime, and k prime. Now, obviously, these 3 vectors cannot be linearly independent, because you can't have 3 linearly independent vectors in a 2-dimensional space. So instead of over here in R3, where the standard basis vectors would generate a nice, clean grid of cubes that would pervade all of space, we would end up with a horribly tangled grid in R2. And because we would have that tangled grid, every point in the grid would have multiple representations. So for example, take this point right here, or the vector corresponding to it. We might say, well, what vector in R3 got mapped over to this point in R2? And because I've only drawn a little bit of the grid here, we might say, oh, well, obviously, we took 1 I prime step and 1 j prime step. So the corresponding vector from R3 must have been 1 I step and 1 j step. So something like this, right? Well, not so fast. That point would indeed get mapped there, but it's not the only one, because 1 I prime step and 1 j prime step is not the only way to get to that red point, thanks to the horribly tangled grid we would get over here, a result of that linear dependence. For example, I could also reach that point by taking 1 k prime step and then 2 I prime steps, which means that if I took the analogous steps over here back in R3, a k step and then 2 I steps, I would have another point that maps to that point in R2. And in fact, it gets worse, as we discussed back in an earlier chapter. When we have a tangled grid like this, generated by linearly dependent vectors, every point in the space can be represented in infinitely many different ways as linear combinations of the linearly dependent vectors, which means there would be infinitely many points over here in R3 that would get mapped to that one red point. And in fact, we will see in the next video, when we talk about the notion of the kernel of a linear map, that all the points in R3 that get mapped to that one point will live on a line. There is a line's worth of points that get mapped to that one point. The importance of which, for us, is simply that it should now be crystal clear that this map, that this matrix, is not invertible. There's no unambiguous way to retrace the steps of a point in the range to find out where it came from in the domain. There are infinitely many points that get mapped to that one point in the range. Anyway, something like this always happens if we have a non-square matrix. We end up with some sort of dimensional collapse, either going forward, where the dimension of the input space is greater than the dimension of the output space, or backwards, if the reverse is true. One way or other, we get dimensional collapse, and when that happens, we always have lots of vectors in the larger space getting crunched into a single vector in the smaller space. As soon as you have that, there's ambiguity in how you get back, which means that there's no inverse. And consequently, non-square matrices are non-invertible. Now, typically it's built into the definition that when we're looking for invertible matrices, we're only talking about square matrices, but I figure you probably want to know the backstory of why we make that restriction. Oh, while I have these pictures here, I'm going to show you something pretty interesting, which I can't explain at this point, but we'll do so in the next video. Consider this a preview. So in the setup here, I told you, I just asserted it, again, I didn't prove it, but that all the points on this line would get mapped to one point right here. And I showed you why that was true for at least two of the points on the line. Well, there's nothing special about that point. It turns out that every point here in the range will be the image of infinitely many points from the domain. But what's neat is that there's a very simple geometric arrangement that falls out of this. For example, let's look at this point at the tip of K prime. Well, we know one point that's going to get mapped to it. That's going to be the point over here at the tip of K. We know that because linear maps preserve linear combinations. So if we have one K step here, we'll get one K prime step here. Everything shows up in the same place on the grid. It's just that the grid is very tangled on the right. Anyway, what's neat is that the rest of the solutions, the other infinitely many points like this one, that get mapped to that point over here also all lie on a line, and that line will be parallel to that other line. It will look like this. And similarly, if we took another point in the range, like say the origin, well, the set of all points in R3 that get mapped to the origin will be another line parallel to these lines. In fact, we know that every linear map sends the origin to the origin, so the set of points over here that get mapped to the origin will be the line that passes through the origin and is parallel to those two lines. So it'll look like this. Anyway, we will prove this all at the end of the chapter we're currently working on. But just as a taste of things to come, I thought you'd be interested in seeing how it works. How we get, in this case, lines getting mapped to individual points, and all the lines are nice and parallel. It kind of shows you the dimensional collapse in a way that you can almost start to feel. It's like you could imagine kind of picking this thing up and moving it around in space so that the various lines get slotted into those points. But anyway, more on that when we talk about the so-called kernel of a linear map, or the kernel of a matrix, which we will do the next time I am lecturing at you. But what we need to do for the rest of this lecture is to discuss how one actually computes an inverse matrix when one exists. I mean, we did it once with a rotation matrix, but that was easy because we had a simple geometric characterization of the inverse, so we could do it from first principles. But if I were to just write down, say, some 3x3 matrix like this one, and I were to ask, is it invertible? And if so, what would its inverse look like? Well, at this point, we really wouldn't know where to begin. Well, actually, that's not quite true. We could figure out whether or not this thing is invertible just by thinking about it a little bit geometrically and then maybe doing some calculations. And if we do that, it will turn out that this thing actually is invertible. But as to how we would actually compute A inverse, well, that's not so obvious, but we'll figure it out without too much trouble. You know, in fact, while I'm thinking of it, I wasn't intending to do this, but let's answer that first question. We'll answer it in a different way later, but just as a review of some crucial ideas that we've encountered in this course, let's answer the question, if A is this 3x3 matrix, is it invertible? Now again, as I said, we'll know how to do this in different ways soon, but just as a quick review, let's think about it. We've never done a problem like this before, so it's not that kind of a review, but it's a review of some really fundamental ideas, both geometric and algebraic. Okay, so we know that a matrix corresponds to a linear map, and this is a 3x3 matrix, so it corresponds to a map from R3 to R3. And we know how the map works. It's going to take the standard basis vectors of R3 and map them to 3 other vectors in R3, namely the vectors given by the columns of the matrix. Now, I'm not going to try to very carefully locate those 3 vectors on my very crude drawing. I don't have to be so careful here. I just want you to think about what could or could not happen, because the results, broadly speaking, will fit into one of 2 broad categories. These 3 standard basis vectors will either be mapped to a set of 3 vectors that are linearly independent and therefore generate a clean grid of parallel epipeds that fill all of 3-dimensional space. So either something like this, or it could send them to 3 vectors that are linearly dependent. Like here, I have tried to draw them so they all lie in the same plane through the origin. And if that happens, they don't generate parallel epipeds at all. We get a horribly tangled grid in that one plane. Now think about what we were just talking about. This is coming together nicely, by the way. In the first case, if those vectors are linearly independent, we do not get any dimensional collapse. We just get a nice, clean grid transformation. And every point in R3 will have its very specific mate in the original version of R3, in the domain. Whereas, if this happens, we get that dimensional collapse. And every point in this plane will be hit, so to speak, infinitely many times by points in the domain. There will be infinitely many points in the domain that get mapped to every individual point in that plane, which means that we can't get back, which means that the map would not be invertible. The moral of the story is that just by thinking about this geometrically, we see that matrix A will be invertible if and only if, that's what my double-headed arrow means, A's columns, which of course are the images of the standard basis vectors under the linear map, are linearly independent. Be sure you understand why this is so. It just comes from simple geometric visualization of what happens in the linearly independent case versus the linearly dependent case. So now we've reduced our question to another question as to whether these 3 particular column vectors are linearly independent. Well, there's different ways to figure that out, but let's review one that we have talked about. Quite some time ago, we came up with what I called an alternate characterization of linear independence, an algebraic characterization of it, which was that vectors are linearly independent if there's only one way to take a linear combination of them and get the 0 vector. So we could say that those columns are linearly independent if and only if the only linear combination of A's columns that is equal to the 0 vector is the trivial one, i.e. where all the weights are 0. In other words, 0 copies of this column plus 0 copies of this column plus 0 copies of this column obviously gives us the 0 vector. If that's the only way to get the 0 vector, then that means the columns are linearly independent. Basically, it's just saying that these columns generate a nice clean grid. So of course there's only one way to get the 0 vector. But is that true? It's not so easy to visualize vectors in R3 and say, oh yeah, I think they're linearly independent or not. Well, how can we tell? Well, let's recast this in algebraic terms. Linear combinations of A's columns. Well, what do we know about linear combinations of the columns of a matrix? That's what we get when we do matrix vector multiplication. If I multiply this matrix by some vector x with 3 components, then those components become the weights for the columns in a linear combination. So this statement could be recast as saying the only solution of ax equals 0, this equation, ax equals 0, this thing is equivalent to saying the only solution of that equation is the 0 vector itself. Be sure you understand why those 2 statements are equivalent. Matrix vector multiplication is just taking a linear combination of the matrix's columns. So we're saying the only such linear combination that is equal to 0 is the trivial one, i.e. when that input vector, which consists of the weights in the weighted sum, are all zeros. Now, why is this helpful? This is helpful because we know how to solve equations like this. This is just ax equals b. This is solving a linear system. Let's do it right here. Actually, first let me rope this off and have a little room. So I can take this equation, that linear system, and rewrite it as an augmented matrix, like so. Be sure you understand how that works. And now to solve that system in this new form, what are we going to do? Well, we just do the usual Gaussian elimination. And I will leave the details of that to you, but if you carry them out, if you put that thing in reduced row echelon form, you will find that you get this. And now we can read off the solutions, or rather solution, which is just 0, 0, 0. So what we have found is that, yes, the only solution to that equation is the 0 vector, which means that the only linear combination of those columns equal to the 0 vector is the trivial linear combination. And therefore, A's columns are linearly independent. And therefore, this matrix will be invertible. Hooray! All right, this was a good digression because it allowed us to review some important things and grapple once again with that interplay of geometry and algebra. But still, we're left with the question, okay, good, we know it's invertible, and that's a good start. But what actually is the inverse matrix? I mean, can we compute it? What are its entries? We will find that out very shortly when we develop an algorithm for computing inverse matrices. But before we do that, I just want to mention that it is often important to know whether or not a square matrix is invertible, even if we do not know what the inverse matrix looks like. More often than not, we will not know what the inverse matrix looks like, and often we won't care. But it turns out that invertible matrices have all sorts of nice properties, and as soon as you know that a matrix is invertible, bang, you know that it has all those other properties. And in the exercises in this chapter, we will start developing the so-called invertible matrix theorem, which is just a list of lots of different properties that are all equivalent to being invertible. So that if you know the matrix is invertible, you know it satisfies all those properties. If you know it satisfies any one of those properties, then you know it's invertible and all the other ones follow. In fact, let's go ahead and introduce this invertible matrix theorem that I just mentioned. If A is an n by n matrix, so a square matrix, then the following statements are equivalent. First, A is invertible. Second, AX equals B has a unique solution for every vector B. And third, the reduced row echelon form of A is the identity matrix. All right, so we need to understand both what this is telling us and why it is true. And once we know that, we will be able to use it to help us come up with our matrix inversion algorithm. So first, quick recap. What is this saying? When I say that the following three statements are equivalent, what I mean is that they all stand or fall together. Either all three of them are true or all three of them are false. That's a useful kind of thing to know because it may be easy to see whether one or the other is true or false. And then once we know, aha, this say is true, then we know that the other statements on the list must be true as well. Or if we know, oh, this is false, I can see that, then we will immediately know that the other things are false too. And this invertible matrix theorem is just being born right here. This is the baby version. Throughout the book, in the exercises, we will keep extending it by adding on new statements and showing that they are equivalent to the stuff that's already there. Eventually, we'll have something like 14 different statements that are equivalent to invertibility. And you could write down even more than that. But for now, let's just start with these three. In the exercises, you'll tack on 3 more. So let's see if we can understand why these 3 statements are equivalent. And we'll do it in pieces. Let's begin by concentrating just on statements A and B and trying to determine whether they really are equivalent to one another, whether each implies the other. We can understand their equivalence very intuitively, just by thinking geometrically. And it goes back to ideas we discussed earlier in this video. We said that for A to be invertible, it can't crush any dimensions. So for example, let's suppose rather than a general n by n matrix, let's suppose A is a 3 by 3 matrix. Well, of course, it takes the standard basis vectors, maps them to new places in R3, and the whole grid generated by the standard basis vectors gets transformed into a new grid determined by the new positions of those vectors. Now, if A is invertible, it should be clear from our earlier work that A cannot crush any dimensions when it's doing that. Because if it did, for example, if all 3 of those vectors ended up in the same plane, then when we crush all of 3 dimensions into that 2-dimensional plane, we would have to have multiple points from R3 getting mapped to the same point in R2, which means there's no road back from that plane to R3. We would not have that one in, one out property because every point in that plane could have gotten there from multiple different places in R3. So that means that the map could not be invertible. Okay, so we know that invertibility implies that no dimensions are crushed. So we would not have all three of those vectors in a plane. Instead, the clean grid of n dimensions over here, I'm drawing it with 3, but you can imagine 17 if you like, the clean grid over here gets mapped to another clean grid over here, pervading the entirety of the space. All of three-dimensional spaces I've drawn it here, or n-dimensional space if we're working with an n by n matrix. So this implies that the transformed grid is clean, no linear dependencies among the transformed images of the basis vectors, and it pervades all of Rn. But once we recognize that, we should be able to understand why Ax equals b must have a unique solution for every vector b. The fact that the grid pervades all of Rn ensures that we will have a solution. It ensures that a solution exists to Ax equals b, because let's say we have, for the sake of argument, here's some point b in Rn, or equivalently, here's the vector b in Rn. Now, how do I know that this equation Ax equals b has any solutions at all? Never mind uniqueness now. How do I know that it actually has a solution? For it to have a solution, that would mean that there's some point in the domain that when I hit it with A, that map, that matrix, the result is going to be b. In other words, something gets mapped to b by matrix A. Well, of course it does, because if the transformed grid pervades all of the space, then this point lies somewhere on that grid. In this case, it looks like maybe we can get to b as follows. Well, from the origin, we can take one yellow step to here, then two blue steps to this point right here, and then maybe 1, 2, 3 green steps to reach b. But we know that linear maps preserve linear combinations. In other words, they preserve positions on the grid even after we transform it. So that means that since we could get to b by taking a yellow step, 2 blue steps, and 3 green steps, then if we took the same steps in the domain from the origin, a yellow step, 2 blue steps, and 3 green steps, we'd have a point that gets mapped to b. In other words, I'd have some vector x that A maps to b. I would have found a solution to the equation Ax equals b. And of course, none of this depended on where b happened to be. It could have been anywhere, since this grid pervades all of Rn. There's nowhere for b to hide. Okay, so now we understand why solutions to this equation have to exist if A is invertible, but I'm claiming that not only do they exist, they have to be unique. Well, that comes from the fact that the grid, the transformed grid, is a clean grid. It's not tangled up. That means that for every point in the space, there's a unique linear combination of those transformed basis vectors equal to it. In other words, there's only one way to get to that point. And as a result, since linear maps preserve linear combinations, that point has only one pre-image, so to speak, in the input space that can be mapped to it, which means that not only does this equation Ax equals b have a solution, its solution is unique. There's only one vector that A maps to b, no matter what b is. So the fact that the transformed grid is both clean and pervades all of Rn does indeed imply, if you understand how to visualize such things and think about them, that Ax equals b has a unique solution for every vector b. Good. So now we understand why invertibility, which is statement A here, implies the uniqueness of solutions to Ax equals b, which is our second statement right here. And in fact, it runs the opposite direction as well. B implies A, because if we have this matrix A that maps Rn to Rn, and we know that Ax equals b has a solution for every b, well, that means that the transformed grid has to pervade all of Rn. I mean, if it didn't, then there would be somewhere where some vector b could hide from A, where it wouldn't get hit by A, where it wouldn't be the image of anything from the input space. But that's not the case. Moreover, if we know that that equation Ax equals b not only has a solution for every b, but that it has a unique solution for every b, that tells us that the transformed grid must be clean, because in a tangled grid, there are lots of ways, infinitely many ways, to get to any point. And if that were the case, then there would be infinitely many ways to get to any point in the input space, which means that there would be infinitely many solutions to AX equals B. So not only does statement A imply statement B, but statement B implies statement A. So forget about this question mark here. Let's replace it with a big check. Good. And one of the things we are striving for in this course is to be able to understand intuitively what is going on. For the most part, I'm not asking you to write down formal proofs, and I'm not writing down particularly formal proofs either. That all has its place, but that comes from having a deep understanding, a deep intuitive understanding of what's going on, which then you can translate into the language of formal mathematics. That's not our concern here. The concern is developing the intuition, which is what allows you to think fluidly about this material. Okay, so we've made progress. We understand that these first two statements are equivalent to one another. And that means that we can think about statements A and B as a single unbreakable package. If you have one condition, you get the other one. If you don't have one, you don't have the other. They stand or fall together. And now the trick is we have to think, okay, I've got this little package of equivalent statements. I want to show that they are equivalent to statement C. Is that so? Is it true that if the stuff in A and B is true, then I automatically get that A's reduced row echelon form is the identity matrix? And is it true that if I know that A's reduced row echelon form is the identity matrix, do I get this other stuff? It is true, but we want to understand intuitively why that is so. Well, let's start with our little package A and B and try to understand why it implies that C, the third statement, is also true. Well, the relevant piece of the package is B, because if we have a unique solution for every equation AX equals B, it follows that if we produce the augmented matrix with A on the left of the bar and B on the right, and do Gaussian elimination to put it in reduced row echelon form, then from whatever we get at the end, we will be able to read off a unique solution, one and only one solution, where we'll say the first variable is 3, and the second variable is 5, and the third variable is 8, and the fourth variable is 9, and whatever. And the only way that happens is when we have something like this on the left side, while the right is just some column of numbers, because then we have the first variable is the first number, the second variable is the second number, and so on and so forth, till the last variable is the last number, and that would be the unique solution. But of course, that stuff to the left of the bar is simply the identity matrix. And now we can see why this last statement must be true, because if there was no augmented matrix, if we were just working with A and row reducing it, well, we would still get I. We would still get the identity matrix. There just wouldn't be that column that follows it. So the reduced row echelon form of A would indeed be the identity matrix. So we see that if we have this little package, the first two statements, well, that includes the second statement, the unique solution for AX equals B, that's enough to imply that A's reduced row echelon form must be the identity matrix. And does it work the other way around? Can we go from C to our package of A and B? Yes, we can, and that's easy to see, because if we know that the reduced row echelon form of A is the identity matrix, that implies that something is true about this system of linear equations, AX equals B. Because if we were to write it in augmented matrix form and then do Gaussian elimination to put it in reduced row echelon form, we would get, of course, the reduced row echelon form of A on the left of the bar, and the right would be transformed by all those row operations into some column vector or other. But we've said that the reduced row echelon form of A is the identity matrix. So that would be the identity matrix on the left of the bar. And of course, when we have something like that, the identity matrix on the left, well, we can read the solutions off, just like we said before, because we'd have the first one would tell us that the first variable is whatever that number is, and the second one on the diagonal would tell us that the second variable is whatever number that is, and all the way down. And that would be that. And the components of that column vector to the right of the bar would be the components of the one and only solution to the equation AX equals B. And so now we have seen why statement C implies statement B. So in my little picture over here, I go from statement C all the way back over to B, and therefore A as well, because those two are bound by an indissoluble link. So that means that all three of those statements are linked in a single package. They are indeed logically equivalent. They stand or fall together. And now I hope you have a feeling for this invertible matrix theorem. And in exercise 31 in the book, in chapter 4, you will extend it to include 3 more statements. A's columns are linearly independent. A's columns span all of Rn, and A's columns constitute a basis for Rn. I'll leave it to you to explain why you can add those to this list of equivalent statements, which, as I said, will grow from the 3 we explained here out to, I believe, 14 by the end of the book. Consider it one little sub-theme that is going to be running throughout the remainder of the course. But now, after this fairly lengthy but important digression, let's talk about the matrix inversion algorithm, and when I explain why it works, I will be able to do so by referring to this invertible matrix theorem. Okay, so I think what I'm going to do is to begin just by telling you what the algorithm is, and we'll look at a concrete example as well. After we've done that, I'll come back and explain why it actually works. So let's begin with the algorithm itself, the matrix inversion algorithm. If A is a square matrix, we form an augmented matrix of a peculiar form. We put A on the left side of the bar, and the identity matrix, not just a vector, but a whole matrix on the other side of the bar. Once we've done that, we use Gaussian elimination to boil it down to reduced row echelon form, which will look like, well, whatever A's reduced row echelon form will appear on the left, and on the right, that'll be some matrix, the result of taking each column in the identity matrix and performing all the transformations that are required by the steps we take in the Gaussian elimination to bring A down into reduced row echelon form. The result of this operation is the following. If the reduced row echelon form of A is the identity matrix, so if we get the identity matrix on the left, then the matrix we get on the right will be A's inverse. And if the reduced row echelon form of A is not the identity matrix, then A is not invertible. And that is the algorithm. I'll quickly explain how it works in practice, and then we'll explain why it works. So as an example, let's go back to that 3x3 matrix we worked with earlier. If A is this matrix, whose columns are 1, 2, 3, 1, 3, 8, and 1, 2, 2, find its inverse. We already demonstrated that A must be invertible. Mainly we did that as a review of old concepts, which was very timely because it actually led us to important ideas that we have used since. But we weren't able to actually come up with the inverse matrix. According to this algorithm, we should be able to produce it as follows. Form an augmented matrix with A on the left and the identity matrix on the right. And now we just start doing row reduction. We've got a 1 in the right position already, so we're going to need to subtract 2 copies of row 1 from row 2 and 3 copies of row 1 from row 3. We get this stuff, and we already have a pivot in the next position we want. So carrying out the expected row operations then gives us a new matrix where we have zeroed out the second column, and I'll need to shrink this down for the sake of board space. Oops, I do need to see that matrix. We'll change this -1 to a 1 by scaling the third row by -1, which gives us this. Now I'll shrink that guy again, and we're nearly there. All that remains is to eliminate that 1, which we can do by subtracting row 3 from it. In doing that subtraction, we get 1, 0, 0 on the left and 10 minus 6, 1 on the right. Well, our matrix inversion algorithm tells us that since we have reached the identity matrix on the left as our reduced row echelon form of A, then the stuff on the right must be the inverse matrix. So A inverse is going to be that matrix. And in case you're thinking, I just made up this algorithm out of whole cloth, since, after all, I haven't justified it to you yet, you could always, at least as a quick check, take this proposed inverse matrix and multiply it on either side by A itself, and I'm not going to carry out the details here, but if you do, you will find that you do indeed get the identity matrix, as of course you should. And that's how it works. Very easy to use. Easy, but tedious. Now, if we had taken some other matrix that was not invertible, and we tried to carry out the matrix inversion algorithm, it would let us know that the matrix was not invertible, because we would finally end up with a matrix on the left-hand side in reduced row echelon form that was not the identity matrix, and that would be our signal that we were trying to invert a non-invertible matrix. Okay, but where does it come from? Why does this thing work? Well, I will explain. For the moment, forget that you've ever heard of it. And down here, let's just pretend that no matrix inversion algorithm has ever been created, and it is our job to come up with one. We're going to grope our way through the darkness down here and come up with an algorithm. And at the end, we will see that it is indeed this one. So, given some matrix A, we want its inverse. What is that inverse going to look like? Well, what do we know about it? We know that A times A inverse is the identity matrix, and that might be enough to at least give us a toehold on the problem. Really? How is that going to help? Well, we do know something about how matrix multiplication works. And remember back when we first learned about matrix multiplication, you learned two perspectives on it. There's the entry perspective that we use all the time to compute products of specific matrices, but there was also the column perspective on matrix multiplication, which I said is often very helpful in developing the theory of linear algebra. Well, this is one of those places. To use it, I'm going to have to give names to the columns of A inverse. So if we let A inverse be, well, let's call the columns x1, x2, all the way down to xn. If we do that, then by the column perspective on matrix multiplication, we know that A inverse is going to be a matrix whose first column is A times the first column of A inverse, and whose second column is A times the second column of A inverse, and so on and so forth, all the way down to the last column, which will be A times the nth column of A inverse. You can review that column perspective on matrix multiplication if you need to. Okay, so far so good, but does this help us, or is this just introducing some new symbols? Well, no, it does help us because we know that this, which is A inverse, is equal to the identity matrix. So that stuff is equal to the identity matrix, which, if we expand it out, we could rewrite as the matrix whose first column is the first standard basis vector, E1, and whose second column is the second standard basis vector, and all the way down to the nth standard basis vector for Rn. So this equation right here is just another way of saying that A inverse is equal to the identity matrix. But this is going to be a very useful way of thinking about it for us, because instead of just thinking about it on this large level of the matrices themselves, now we can say, well, all right, if these two matrices are equal, that means that all of their corresponding columns have to be equal. So in particular, it would tell us that A times x1 is E1, because the first columns have to be equal, and A times x2 is equal to E2, because the second columns of the matrix have to be equal, and so on all the way down the line. Now, if the backstory here was that we were trapped on some desert island by an evil genius who would not let us off until we had discovered an algorithm for inverting matrices, essentially, we could get off the island now. Because look at what we've got. These n equations, well, those are really n systems of equations. And we know how to solve systems of linear equations. So for example, if we solved this one, we would figure out what is x1. And x1, don't forget, is the first column of our inverse matrix that we're trying to construct. So we could solve that system and we would have the first column of our inverse matrix. Then we could solve this second system for x2 and we would have the second column of our inverse matrix, and continue on. And at the end of the day, we would have solved our nth system of linear equations, and its solution would be the nth column of the inverse matrix that we are trying to construct. So our matrix inversion algorithm, the world's first in our little story, could be, here's how you invert matrix A. First, you form AX equals E1. You solve that system, and that is your first column of the inverse matrix. Then you solve AX is E2. That solution is the second column, and so on and so forth. You solve AX equals EN, and that is the last column of your inverse matrix. Put all those solutions together, and you have your inverse matrix, and you're done. And that's a perfectly good algorithm. I mean, good in the sense that it works. And on our desert island, we would be ecstatic that we found it, because we would be going home soon. But here, in our comfortable homes, we're liable to look askance at it and say, yeah, that would work, but it's bad enough that in the matrix inversion algorithm that I just showed you, you have to do this Gaussian elimination business once. Here you'd have to do it n times. I mean, what if it's a really big matrix? It would take forever. Well, look, the way algorithms tend to develop is somebody starts by finding an algorithm that works, but is crude, and then somebody polishes it and gets one that not only works, but works more efficiently, and so on and so on and so forth. The inversion algorithm that I showed you really is just a polished version of this one right here. The idea is that if we were going to actually carry this out on our desert island, what we would end up doing is we'd form all of these augmented matrices, n of them, and we would put them all into reduced row echelon form by Gaussian elimination, and for each one we'd end up with the reduced row echelon form of A on the left, and on the right we'd get some column. Same story for the second one, and all the way down. We'd get different things on the right-hand side, but we'd always end up with the reduced row echelon form of A on the left. Now, if we assume for a moment that our matrix A is in fact invertible, since we're looking for its inverse, if it's invertible, then we know by the invertible matrix theorem that these reduced row echelon forms of A would all be equal to the identity matrix. And if that were so, then these columns on the right-hand side of our augmented matrices would represent the solutions to the corresponding system. But of course, the solutions to those systems, x1, x2, all the way down to xn, those are the columns of the matrix we seek. So these are going to be x1, x2, and all the way down to xn. We would pluck them off, stick them in a single matrix, show them to the evil overlord of the island we're trapped on, and go home. But once we got home and we were reflecting on what had happened to us, it would probably occur to us, we didn't actually have to go through that n different times, because all the steps it took to reduce A, the original matrix, to I, the identity matrix, those are the exact same steps we ended up doing again and again and again and again. And we didn't care because we were just so happy to be actually inverting the matrix, even if it took a long time to do it. But if we ever find ourselves doing such a thing again, we could save time by doing it like this. Combine all that stuff. Let's make a single augmented matrix with A on the left, and then on the right, let's not just put E1 or E2, let's start by putting them both there. And if we just started like that, we'd recognize that when we did the row reduction, A would boil down to the identity matrix, of course. And as we did so, all those steps we took to get A down to I would be pulling E1 down to x1 and E2 down to x2. And we wouldn't have to go through all that torture twice. And in fact, there's no reason to stop with just 2. We could put all the columns there. And essentially what we'd be doing now is solving n systems of linear equations simultaneously. AX equals E1, but we'd also be solving AX equals E2 and AX equals E3, and all of them up to and including AX equals EN. And when we carry out the row reduction, we'd still get the identity matrix on the left, but then on the right, those columns would turn into the solutions of those n systems. We're just doing them all together rather than separately. But those solutions, x1 through xn, of course, that is going to be the inverse matrix, which is what we were after. And now we can see why this matrix inversion algorithm that I showed you before does indeed produce the right thing. And I should also mention for this second case, if we try to do it on a non-invertible matrix, well, going back to our desert island situation, when we tried to carry out those row reductions on our n different systems of linear equations, we would find each time that the A stubbornly was not converting into I. Again, that's just the invertible matrix theorem. If A is not invertible, its reduced row echelon form is not going to be I. Okay, so that explains why this algorithm actually works. A few last notes on it. In theory, one way to solve a system AX equals B is to proceed in what would seem the algebraically obvious way. Namely, since we're trying to figure out what X is, we want to isolate it, like in high school algebra. But we can't divide by a matrix, of course. But what we can do is get rid of that matrix on the left-hand side by multiplying both sides of the equation on the left by A inverse. That's nice because A inverse A is, of course, the same thing as the identity matrix, and the identity matrix times X is, of course, just X. So in one sense, we're done. Hooray! Well, okay, it looks nice and neat as algebra, but there are serious practical difficulties. If you wanted to do this with a concrete, specific matrix, to carry this step out, you actually have to have the inverse matrix. And if you don't have that handy to begin with, you have to compute it by using the matrix inversion algorithm. And that inversion algorithm is computationally expensive. It takes a lot of steps to carry it out if your matrix is a large one. Like let's say if this is a 100 by 100 matrix. If you ask a computer to first compute the inverse matrix by doing this algorithm, and then multiplying this vector by the inverse matrix to get the solution, it'll get you there, but it requires a lot more computation for the computer to do than if you just did the usual Gaussian elimination, reducing it to row echelon form, and did back substitution to get the solution. Another advantage of that latter approach is that even if X is not invertible, like maybe this thing has infinitely many solutions, right? We know from the invertible matrix theorem that the uniqueness of the solution is equivalent to the invertibility of the matrix. So if we have infinitely many solutions, and thus this thing is not invertible, forming an augmented matrix and doing Gaussian elimination, boiling it down to row echelon form, we'll still put it in a form where we can write down all infinitely many solutions, like we did in the previous video. But if you asked the computer to solve this by computing the inverse matrix and then multiplying b on the left by that inverse matrix, it's not going to work because there isn't an inverse matrix. So last thing I should mention is that in the case of 2x2 matrices, there's a very simple recipe for writing down an inverse matrix, and you will see that in the exercises in the book. That is one you should know off the top of your head because it does come up pretty frequently. All right, I think that does it for this lecture. I will see you next time. Well, strictly speaking, I will not see you next time, but you will hear me next time. Goodbye.